Descriptive metadata can also be exported as a JSON file. A rule to export descriptive metadata as a JSON file is available in LifeLibeZone Home RWMore rules dmp-json.r. This is one of the formats that can be used to export metadata. Other formats include pipe delimited text files, an XML file, and a keyword value text file. The metadata for each file is stored in a separate JSON file within the data grid. The organization of the JSON metadata files was changed for this rule. Instead of storing a metadata file in the same collection as the original file, all of the metadata files are stored in a new metadata subcollection that is created within the original collection. This helps improve management of the derived metadata files. As before, the AVUs for each file are saved: metadata adder name, metadata adder value, and metadata adder units. The rule assumes that there are no special characters in the AVU names, values, or units. The special characters for JSON files include a single quote, a double quote, a backspace, /f, /n, /r, and /t. N is the new line, R is return, and T is a tab. The rule could be modified to encode special characters using the policy function JSON encode. This policy inserts a backslash in front of each special character in conformance with the JSON specification. A JSON file has the following structure. The data name for the file is defined, and then all of the metadata attributes for the file are listed under metadata. A separate metadata file is created for each file in the collection. That metadata file holds all the metadata attributes associated with the file. In this example, there are 3 metadata attributes. Metadata attributes that do not have a units field have a null written for the value. The rule used to create the metadata file is listed here. The rule uses 2 input parameters. *call is the full path name to a collection in the data grid. *res is a storage resource name with the default value demo resource. This will need to be changed to LifeLib resource 1 for the lifetime library. The rule calls 2 policy functions to verify the input values: check call input and check resource input. A metadata collection called metadata is created as a subcollection within the *call collection. All of the metadata files for the *call collection will be stored in the metadata subcollection. A query is constructed to retrieve all of the files in the *call collection. A loop is made over the result list to process each file. For each file name, *file, a separate metadata file is made with the name file.json. A query is constructed to retrieve all of the metadata attributes for each file. The rule loops over the returned metadata values, writing the metadata in the JSON format into file.json. The process is repeated for every file in the *call collection. To create a version that encodes special characters, use the following modifications. We retrieve the attribute name. We can then invoke the policy function JSON encode to automatically insert backslashes in front of all the special characters and save that in variable *n. We do the same thing for the data attribute value and the data attribute units. We can then write to the output file *l file the encoded versions of name, value, and units. This would then protect you against special characters within either the attribute name, attribute value, or attribute units. Take 7 minutes and complete exercise 64. Create JSON files containing metadata for files in a small collection. Check that you have added metadata to each file. Run the rule LifeLibeZone Home RWMore rules dmp-json.r. The output JSON files will be located in a new subdirectory called metadata. Please load a paragraph describing your results into the lifetime library in the subcollection class INLS 624 by the end of today's class. Bayer Healthcare is exploring ways to manage genome information in production systems that support multiple research projects. Bayer is a participant in the IRODS consortium. Bayer is applying the IRODS data grid technology in support of massive genome collections. At the IRODS user group meeting in 2015, they presented information about their approach. They chose to implement a production genomic data grid that was backed up by a development system and an acceptance test system. Before they could use new data management systems in production, they had to evaluate the effectiveness of the software locally, check for bugs, and check for security holes. They could then implement an acceptance test environment which emulated the production system. The acceptance test had to evaluate scalability, performance, and load management. Once these two steps were passed, a production version could then be implemented. The challenges faced by the production system are similar to those encountered by other groups building research collaboration environments. They included managing data security, multiple projects, each with different sets of researchers needed access. This required organizing researchers in groups with overlapping membership between groups. Managing information. The provenance, access restrictions, project annotations, and tags had to be persistently linked to each data object. Bayer handled this by creating a schema, a set of standard metadata attribute names that provided a superset of the information needed by each project. Data ingestion. Since sequencers can run 24 hours a day and multiple sequencers are used, data ingestion had to be automated. The data had to be deposited into the IRODS collection and also deposited into a high-performance computing file system for analysis. Redaction. Each time a genome was processed and combined with other genomes, information had to be tracked and automated. By keeping explicit information on every data set, audit trails could then be processed for redaction of data after any processing step. This is necessary when a patient may decide to have their data excluded from a specific project after they originally approved use. From the perspective of a patient, their genome is essential data that should control treatment for diseases. From the perspective of a drug company, the analysis of common drug performance requires the integration of information across a large number of genomes. Thus, drug companies build patient cohorts that have common diseases and analyze the properties of the genomes across the entire cohort. The data may be reused for multiple analysis projects, may be combined with genomes from other cohorts, and may still contain protected data. The standard practice is to first get informed consent from each patient for the use of their genome. Their genome can then be used within a cohort. However, a patient has the right to change their mind at any time and ask that their genomic information be removed from a project. This requirement for data redaction was implemented by tracking the chain of custody of each genome and tracking the use of each genome in each project. When data are distributed globally, the tracking had to be done across every storage location. Data grid technology was used to enforce the ability to redact patient cohorts for distributed data collections. Auditing mechanisms were used to track the data from each patient through each analysis workflow. This made it possible to maintain a chain of custody, not just storage location, but also use by a project for data from each person. The chain of custody was turned into annotations on the patient data. The annotations could then be curated to provide a standard reference identifier for each patient. This is strongly related to provenance for workflows. What are the input data for each analysis, and how are the input data related to the output data from the analysis? The privacy mechanisms of the IRODS data grid were used to track the chain of custody. A separate user group was created for each project. Access permissions were then managed on each dataset. It is worthwhile to think of the annotations on the datasets as tracking access permission for the original patients. The intersection of file access permissions for the researchers with the annotations of the chain of custody for the patients then defines what datasets can be processed at any point in time. The usage can be controlled even when datasets require redaction. The challenges addressed by Bayer were all manageable using data grid technology. This virtualized collection properties, enabling access controls to be applied at distributed locations on heterogeneous storage systems. The ability to support annotations on files enabled the tracking of the chain of custody. The ability to create workflows and track the provenance of workflows is a generalization of the Bayer approach.